So you can do fully fledged networking from your microcontroller, which is also something in the C world. There are some libraries doing this. They all work differently. Here we have one common implementation for this ecosystem that just works. Thank you all. It's an honor of being here, of speaking here. I've been at this meetup for quite some time, quite around and talked to some people, and I'm really happy to share a talk with you today. So what I'm going to talk about today is Embassy. And the subtitle, Running Rust on Embedded with Async Tasks, basically tells us what this is all about. And if you've been into async Rust, you probably know it from a whole different context and ask yourself, well, is this actually a good idea to run async Rust on such a tiny embedded device when I'm more familiar with running it in cloud environments or for web server applications? So I want to start out with a motivation. In a previous talk, we learned about interrupts. In classic embedded programming, these signal events that the main program awaits. And this naturally transfers to the use of state machines. So if you're modeling an embedded system, you often meet state machines for subsets of a program or for whole programs. So let's make a simple example of a state machine and check whether we can actually do better doing it in an async version than in a sync version. All right, imagine we have a device, and this device has two LEDs. One LED that should blink every 500 milliseconds, and one LED that should toggle based on a button press. So a state machine implementation of this could look like this for the first part. So this notation is basically, you have this big black circle, which is the starting point of the state machine, and from there on we immediately transition to the first state, which is LED 1 on in this case. And the annotation on this transition basically says the thing before the slash is the event that happens, the thing after the slash is the action we take. So in this case, we're just turning the LED 1 on when we enter the state machine. And then we can toggle it every 500 milliseconds by just saying, okay, after 500 milliseconds, turn the LED off, transition to LED 1 off. After another 500 milliseconds, do the vice versa thing. All right, and now let's put in the second LED. Well, we can do so by just having another part of the state machine. And whenever it starts up, we turn the second LED on, and whenever the button is pressed now, we toggle and switch states. So obviously this is a non-deterministic state machine. And non-determinism is something that's really bad for programming, actually. We could implement this if we would have an OS running on our microcontroller by using 2 threads, for example. But we want to do this in a more restricted environment. Like, okay, we are in Rust. We are in a no-std environment, means we don't have allocation, we don't have threads, we don't have OS support. And for portability reasons, we do not want to drive outputs from interrupts, which is something you can obviously do. So how are we going to run these two things in a no-std environment with these constraints, with basically just one thread of execution? And the answer to this is we transform it into a deterministic state machine. This is also something that is really common in classic embedded programming, which you will see if you have a complicated thing that you're going to model, you model a non-deterministic version and then transform it into a deterministic one. So how would this state machine look as a deterministic state machine? We have again, when we start up, an action that turns on both LEDs in this case. And we already need to make a trick here. We need to use a variable for time tracking. In this case, this variable is called remaining, and we set it to 500 milliseconds. And now we do the same thing as basically in the previous example. So after the 500 milliseconds, in this case after remaining, because we need the variable to track the time, we turn the first LED off, transition to the next state, and reset the counter. For the button, it's quite similar, but now we actually need to do the time tracking here too. Yeah? So whenever the button is pressed, we turn the second LED off, we transition to the new state, but we need also to reduce the remaining time by the time that we spent in the previous state. And here you already see something that can become really problematic. Yeah, you need to do the time tracking yourself if you don't have some kind of sleep function. And well, the completion of the state machine is basically this. It is more or less mirrored down to the bottom right side. All right, how would you implement this? I've prepared an example implementation. I think this, there we go. To turn around a little bit. All right, so this is an implementation of the state machine. We see that the state machine itself is modeled as an enum of states. We see a representation of each state of the state machine that we've seen before. And we also see that each state carries the remaining time as a duration. Now, in this really simple example, we could also have put that remaining time into a kind of global variable. But if you have more complicated examples, then you will have only subsets of a state machine that actually carry these variables. So I decided for this example that we will stick with the way of modeling it, that each state has its own remaining variable. The events that happen from outside are also modeled as an enum, which contains exactly two things: the time that has passed with a duration, or the button that has been pressed. And then the whole implementation of the state machine looks like this. It's a single function that takes in the previous state, the event that happens, the first LED pin and the second LED pin. Now these two are actually output pins, which is a trait from embedded HAL that Dominic already told us about. So we can drive the GPIO pins with that. The concrete implementation now is just a single match statement over the current state and the event that is happening. You can imagine this like a table where you list all possible states against all possible events, and in each cell of the table you fill in what is going to happen. And the implementation that we see here is now basically this, just that this table is unrolled step by step. So, for example, if we are in the state where both LEDs are on and we get an event that some time passed, then we need to check, okay, has remaining expired? If so, this is the else case in this implementation. We toggle the LED and we transition to the next state, and we also reset the duration. Otherwise, we just do some time tracking here. For the button, it's a little bit simpler. We just set the second LED to low and transition to the next state, carrying on the remaining variable. And if I just scroll down a little bit, you see that this pattern repeats. Yeah, this all looks quite similar to what we've seen already, and it's quite lengthy, and it only differs in details. So this is quite complicated to implement actually, and quite difficult to get right, because just copy pasting it down and then you forget to change a thing and suddenly your program is doing the wrong thing. So this kind of programming style requires thorough testing, and you still might do mistakes that only happen on single code paths that you forgot to test. So this is complicated and error prone. And can't we do better than that? So let's take a closer look at the motivation we've seen before. And I'm going to highlight some words now. In classic embedded programming, interrupts signal events that the main program awaits, and this naturally transfers to the use of state machines. Now, seeing these three words highlighted there, I can also tell you this also naturally transfers to async Rust. Why is that? Well, the answer to this is that async functions are actually state machines. So we can make use of the async ecosystem to actually model state machines. And we can write embedded programs with that. Let's have a look at what the Rust compiler sees when it sees an async function. Each async function desugars into three things. First, an enum representing the possible states of the function body. What are the possible states? Well, we have some state that says, okay, this function has not begun running. Then we have a state for each await point inside an async function. And finally, we have one state for the case that this function has run to completion. The second thing that's getting generated is a function creating the initial enum variant from the function argument. And this is basically a sync version of the async function that we originally wrote. All the parameters that we pass into that async function are passed on to the initial enum variant. And then we have an implementation of the future trait, which has a single function called poll. And poll runs the function body as a state machine. So each time poll is invoked, it makes some progress on the state machine until this has finished. And if we're looking at these 3 points now and compare it to the example we've seen before, then we see that it's quite similar. We also had an enum that represented the possible states of the function body. Well, we didn't actually have a function that created the initial enum variant, but we for sure need to create it somewhere. We just didn't see it in the example. And we also had a function that was running the actual implementation, so the function body as a state machine. So this pretty much maps to the manual implementation we've seen before. If you're interested, all of the above can be derived from the mid-level intermediate representation emitted from the Rust compiler. I've done some reverse engineering on that, and you find it in the supplementary material to this talk. All right, so we've now seen an async function desugars into these things, but someone needs to call the poll function. And who is that? Well, async functions do nothing unless they are polled. Yeah? So the desugaring just creates a function that creates an enum variant that is not executing any of the actual code that we wrote. That polling that we require to actually run the function is done by a component that's called the executor. And this executor is not part of the Rust runtime itself. So in other programming languages, in Go, for example, the executor is brought to you along with the compiler as part of the framework that the programming language provides. In Rust, this is not the case, because in Rust, the decision was made that applications may choose the executor that's the best fit for them. So if you're running on a web server, you will probably choose a different executor than when you're running on an embedded device. Some common examples of executors include, for example, Tokio, which is a work-stealing multi-threaded executor that's specifically targeting web server loads. Then there's Glom.io, which is a thread per core executor also targeting all the web world, although they have benefits over Tokio in very specific workload situations. These two are requiring STD. So this is probably something that you never want to run on a microcontroller. And then there's the Embassy executor, which is actually the most interesting thing for this talk today, because this is an executor specialized to embedded environments. And this is exactly the thing that we want to see today. Now, how would an async version of that example look that we've seen before? I'm just scrolling through that once so you can see that this program is much shorter than the sync version that we've seen before. It basically consists out of 3 async functions, and all of them are quite short and easy to understand. Let's start at the bottom with this run function. So, by the way, I didn't mention it in the first example. These are library projects in Rust, so this code actually compiles. And you could use it in theory. I wouldn't advise you to, but you could. So this run function here is taking now, again, 2 LEDs, and it's taking a button. So this example actually does more than the previous sync version. It also does the button handling itself. It doesn't give that button handling to the library user. The button is an instance of button pin, which is an implementation of the wait trait, which is coming from the embedded HAL Async crate. And this gives us the possibility to wait for specific electric conditions on a wire. So this is basically an implementation of an async GPIO input pin. And what we do now is we do a select over run LED1 and run LED2. Wait, so this program is actually doing concurrency on a single thread. Because the select function here is going to take two futures. So things that are created by async function calls of run LED1 and run LED2. And then whenever this run function is called, then we call run LED1 and run LED2 alternatingly. So we get concurrency on the same thread. Now, I wouldn't advise you to use the select function that much in production and be careful, but we will come to that in a moment why. Let's have a look instead at the run LED1 and run LED2 functions, because these now pretty fairly resemble what we've seen in the async state machine example. So running the LED is just an endless loop of waiting for 500 milliseconds, toggling the LED, waiting for another 500 milliseconds, toggling the LED again. And running the button-driven second LED is just an infinite loop over waiting for a rising edge, toggling the LED, waiting for another rising edge, and toggling the LED again. So this is much better than before. And this is also the reason why async on embedded really makes sense. You can write really concise, really maintainable and easy to understand programs that are much more complicated to write if you are in a sync environment under the same constraints. As you've seen, what I've omitted in these examples, for example, is hardware initialization. All of this is microcontroller specific, and I wanted to keep these examples as portable as possible. All right, so let's come to the heart of this talk and talk about the Embassy framework. The name Embassy stems from embedded async, and we will start with an overview over what Embassy actually offers to us. I hope you can read this. I expected to have a much larger screen, actually. So if you can read something, just call out and I'll try to help you with that. So the core thing that we have is the Embassy Executor. That's the heart of everything that we're doing. This Executor is implemented in a way that is requiring the core lib only. So this is fully no-std compliant. It also has a fair scheduling algorithm that prevents CPU monopolization by a single task. This has a limitation though. The tasks need to call an await point from time to time because Embassy does fully cooperative scheduling, as it's usual with async Rust. So there is nothing as preemption. Yeah? So a task is not taken away the CPU from it if it consumes too much computation time. Yeah? It needs to call an await point for Embassy to actually be able to interfere with that. What it also gives us is auto sleep if no task is ready. And this is a huge advantage. Especially for battery-powered devices, this is really, really important because you want to save as much CPU cycles as you can and spend them in a sleep state to not consume any power. If you imagine the example that we had before, the sync example, then it's really hard to tell whether you can actually send a microcontroller to sleep or whether there's still some work going on that it needs to complete. And Embassy basically gives us all of this for free. Another notable point is that whenever you call an await, this will, in most situations, schedule an interrupt, then send the task to sleep. And when the interrupt fires, then the task is woken again. So there is no such thing as busy loops or polling in Embassy, at least not if you have a good implementation of the embedded HAL crates. All right. The thing that is actually managed by the executor are the tasks we are going to write. There is going to be a fixed number of them, and they need to be statically allocated at startup. This is a limitation that stems from the fact that Embassy is fully no-std compliant, so there is no dynamic memory allocation. There is no way to dynamically spawn as many tasks as you like at runtime. You need to put an upper bound on that so enough resources can be made available during compilation. Now, from within our tasks, we can go ahead and run some code. And this you usually do through use of the embedded Rust ecosystem. So, for example, by going through an implementation or going through the traits of the embedded HAL or embedded HAL Async. This also means that we can now make use of all agnostic drivers that you can possibly imagine that are based on these trait implementations. But, well, an implementation of these traits needs to come from somewhere. So this is again coming from Embassy. Now you can also see the color coding in this example. Everything that's yellowish is provided by Embassy or the Embassy ecosystem, and everything that's green is provided by the embedded Rust ecosystem. So which chips are actually supported for an implementation of the embedded HAL traits? Well, we have support for the Nordic NRF family of chips, the Embassy RP for Raspberry Pi based microcontrollers. We have basically support for all STM32 chip families, and we have support for the IMX-RT family, with more to come. So in the Embassy repo, they are actively working on adding support for other chips. And what's also notable here, we have support for basically the whole family of ESP32 chips from Espressif through their own maintained ESP-RS project. So this is not actually part of Embassy. This is maintained by Espressif, the vendor of these ESP32 chips. All right. But, well, we do not want always to call through embedded HAL or embedded HAL async to interact with peripherals, and we also can't do that because there are things like hardware initialization. This is really dependent on the chip that we are using, so you will want and you will need to bypass the embedded HAL crates at some point. And also if you have like a really specific peripheral, or you know that the code that you're going to write is only running on this one microcontroller, maybe you're saving yourself the overhead of going through the embedded HAL. Now, Embassy gives us something more than this. For example, utilities. These are utterly important too. The first thing that we have here is Embassy Time. This is for time and timer management, and I actually sneaked something of this already in the previous example, because time is not something that's in core Rust, so you need something that provides the opportunity or the possibility to manage time, and this is Embassy in this case. We also have, as there was the question just, Embassy Sync, which gives us implementations of common synchronization primitives like channels, signals, mutexes, all the stuff that you can imagine that you require to actually do concurrent processing and share memory or send messages in a safe way. Then we have Embassy Futures. This gives us the join and select functions, which are required if you want to run two futures on a single task. And then there's Embassy Boot, which is also really notable because Embassy Boot is a bootloader for power fail-safe firmware updates. I have to say there is limited support for this bootloader, but this is still really great because from experience I can tell you that firmware updates are always complicated, are always scary. Basically every vendor implements them in a different way and every bootloader works in a different way. So having one that's coming from the ecosystem that we are using, that's definitely compatible with the application that we're writing, is a really big fit. And if it's then even power fail-safe, so you don't even have to worry about the power turning off during your update, that's also great. All right, and then there's the second thing that's becoming or has become utterly important in embedded systems. This is connectivity. Because every embedded system today is connected in some way to the environment. Isolated embedded systems that work on their own have become really, really rare. So you will always at least communicate over a wired interface, like doing some UART communication or Modbus or ARS485 or something like that. But Embassy also gives us possibilities to do more complicated stuff. For example, there is Embassy USB. This is a device-side USB stack. And that gives us the possibility to implement serial USB devices or human-computer interfaces, or even define our custom USB profiles so that we can implement our own device that you can connect via USB to a host PC. Then there's Trouble. Trouble is a Bluetooth low energy stack, and well, Bluetooth is a complicated thing because there's the Bluetooth SIG, which requires you to have certification if you want to communicate via Bluetooth. And the Trouble project actually aims for getting this certification by the Bluetooth SIG. The usual way you do this in embedded is that you go to a vendor that has a qualified Bluetooth stack and tell them, well, I want to use your Bluetooth stack, how much money do I owe you? And that's a lot usually. So this is also a really, really great thing. And last but not least, there's EmbassyNet, which gives us basically everything that we need to do network communication. It gives us an Ethernet stack, an IP stack, TCP, UDP, ICMP, and DHCP protocol implementations. So you can do fully fledged networking from your microcontroller, which is also something in the C world. There are some libraries doing this. They all work differently. Here we have one common implementation for this ecosystem that just works. All right, this is a lot to take in. And we've seen some code examples, but none of these were actually running. So how does a real Embassy program look like now? This is now a real Embassy program, and you will see that running in a moment. But let's have a look at this and the differences to the library example that we've seen before. So we see now we have the no-std and no main annotations. Dominic already talked a little bit about them. Then we have some use statements that are really specific to embedded Rust. And then we have the program that consists, again, of a bunch of async functions. Let's start at the bottom again. Now we have a main function that's annotated with the Embassy Executor main macro. This basically marks this function as the entry point into our program, and it hands us a spawner that we can use to spawn tasks. The first thing we do when we start up is we initialize the hardware abstraction layer. In this case, Embassy RP, because this program is targeting the Raspberry Pi RP2350 microcontroller, the one that you can find in the RP Pico 2W. Then, from the hardware abstraction layer, we get some information and use that information to create our pin configuration for a red LED, a blue LED, and a button. So that basically implements the same example that we've been going through the whole talk now, but I switched out LED 1 and LED 2 for a red and a blue LED. Don't worry, or be aware that I have actually used RGB LED for the hardwiring when we see it running in a moment. Then we use the spawner to spawn a second task. This second task is going to drive the red LED, and then we basically hijack the main task to run the button-triggered blue LED. Now, the red LED task that we've spawned below is just another async function that's annotated with the Embassy Executor task macro. And from there on, we just do some ordinary async stuff. In this case, to stay close to the previous example, we call a function that runs the red LED. And then, well, we have these two functions. They look quite familiar to before, but they changed a little bit. So running the LED that toggles all 500 milliseconds now doesn't use plain sleep, but instead uses a ticker. So why is that? Well, when Embassy executes an await statement, then it sends your task to sleep, and maybe when the interrupt fires that wakes up your task, another task is still running. So there might be some delay until your task is actually able to start running. So you will have a slight offset, maybe just 1 or 2 milliseconds. But this will be notable over time. So your LED is not just blinking in a 500 millisecond pattern, but maybe in 502 milliseconds pattern. So what this ticker does to compensate this, it measures time and then just sleeps for maybe 497 milliseconds to compensate for this. And then we have the function that runs the button-triggered blue LED. This also looks familiar. There's just one thing that has been added here, apart from the logging, which is, well, the fact is we're dealing with real hardware now. And these small buttons that you find in basically every embedded device that has buttons have a small problem. This is actually an electrical problem. When you press them, they don't produce a clear electrical signal. They don't jump on the wire from the low level of logic to the high level, but instead they go high, and then they start to jump around between high and low states. So we need to compensate for this in software. And the easiest way to deal with this, it's not the only way, but it's the easiest way to deal with this, is to just say, okay, whenever we detected that the button was pressed, then we wait for a specific amount of time until we are sure that this jumping around on the logic level has stopped, so we don't actually fall through multiple of these cases. Well, and that's the whole magic. So I cannot tell because Dominic's editor is a little bit different than mine. And in just about 70 lines of code, we have implemented something that took, well, let's have a look. It's fine, it's fine. We implemented something that took us almost 100 lines to just implement the logic of Instant Rust. All right, so because we have some online viewers, we only have this as a video and not as a live demonstration. You see now how the code is compiled, and then it's flashed. And now you see it running on the real microcontroller, and there you see me pushing the button. So the blue LED, or the blue part of the LED turns on, while the red part of the LED just continues to toggle. One more note in this video, you see at the start, I don't know if you noticed, that I'm compiling in release mode. If you're targeting embedded targets, especially with Embassy, you should always run in release mode, because async programs tend to become really, really big in debug mode, because there are no optimizations that optimize away all this future polling stuff. So if you want, compile always in release mode. Otherwise, you might notice that your microcontroller is running out of flash memory to store your program.
On the top of the data, is this debugging equipment? Or
Yes. Yes, this is the Raspberry Pi Pico debug probe. This is used to actually flash the program and also get the debug output that you see in the bottom here. This second connection here is just used to power the microcontroller. There is nothing logically going over this micro USB port. All right, for the rest of this talk, let's have a look in more detail at what the bits and parts of this program that we've just seen actually do. So let's start with the crate level attributes and use statements. I will just go quickly over this, although Dominic already gave a pretty thorough explanation of these. So we have the no-std annotation, which means we have the core library only. We don't have std. We maybe have alloc if we bring our own allocator. Then we have no main. No main means the entry point is provided by us. The Rust reference says to this that Rust C should not emit a main symbol for executables, no interaction with the OS, no passing of arguments, and so on. But this also means that a definition of main from somewhere else is required. So in our case, we use the Embassy Executor main annotation on the main function, which will make sure that there is an entry point declared for the Cortex-M-based RP Pico 2. This is because we told Embassy in the cargo toml that I didn't show that we are targeting the RP Pico 2, and it will make sure to create an appropriate entry point for us. Inside this entry point, Embassy will do some minimal initialization, and after that minimal initialization, bring up the executor and spawn a first task on it that calls into our main function. All right, then we've seen some use statements specific to embedded Rust, and at this point I would just rather tell you where Embassy actually lives in this diagram. We've already seen this before in Dominic's talk, and what you see here is basically the same thing. And where does Embassy now fit in here? Well, it basically hooks in at the point where we have the hardware abstraction. Yeah? So Embassy is just another abstraction towards the hardware from our perspective. If you're interacting with the hardware, you can either call through Embassy directly. For example, in the beginning of our main function, if we start to bring up, well, we basically call some Embassy function that does the really initial hardware initialization for us. We could also call through the embedded HAL traits, in which case we might call through Embassy to access the peripheral access crate, which is the same. So there is no magic other implementation of the peripheral access crate in Embassy. Yeah? It's just using the same PAC as a sync program would do. But we still might also call through an embedded HAL implementation that's not part of Embassy. So there is no force that's forcing you to actually use the Embassy implementations of embedded HAL. You could write your own, or you could take one from someone where you say, hey, this is a really cool project and I want to use this rather than the Embassy variant. And you could, of course, also directly call into the PAC, although you have to be really careful what you're doing there to not block Embassy in the things that it's actually doing. All right, what is this embedded HAL async? Also, Dominic told you much about this, so I'm also skipping quickly over this. It's an asynchronous hardware abstraction layer for embedded systems. It enables us to write hardware-agnostic code and drivers, something that's really missing in the C ecosystem. So if you have a C program that has many dependencies, if these dependencies are well written, they bring their own hardware abstraction layer definition that you have to implement, and your program will look like a program core that has a lot of HAL implementations around it. It leaves peripherals that are better modeled as blocking to embedded HAL. Also, Dominic told you about the GPIO example. Driving in a GPIO pin is mostly after initialization just a single register write. It's just not worth it having an async function because that introduces so much overhead that's hopefully optimized away by the compiler that there is no async GPIO output pin trait in embedded HAL. In embedded HAL async, excuse me. And well, yeah, Dominic also told you already that there are more specific peripherals that have their own specific trait definitions that live in own crates. And you should always have a look at your ecosystem when you have a peripheral that you're checking whether there is a common implementation for, there's a common trait definition for this. All right, let's get to the heart of it and talk about the real thing that's interesting here. That's the async execution. So how does Embassy actually execute our task, and what things do we have to consider when we're talking about writing our program and actually implementing it? So, a quick recap. The Embassy executor polls our futures so that they make progress. These futures to poll are called tasks. So there is a set of top-level futures that's always there, that are statically allocated, and these are our tasks. You define them using the Embassy executor task annotation, which reserves the memory that's required for them, which makes sure to register them with Embassy, and allows you to spawn them using a spawner. And the most important part or takeaway here is that tasks must not take generics. This also includes lifetimes. So whenever you have something that carries a lifetime, you will need to pass a static lifetime. That's the only lifetime that's allowed in this context. And this is for the simple reason that we want to really statically being able to tell which tasks are there in our program. If we put a generic on a task definition, then we cannot clearly tell that there is just one implementation, because monomorphization might create 2 or 3 or maybe a dozen. We don't know. The lifetime thingy can become an issue, but usually isn't, as the thing that is mostly passed to tasks is something that depends on peripherals. And peripherals are by definition always there and always have a static lifetime because, well, they are part of the hardware. The hardware is there before our program starts to run, and it will be there after our program stops to run. At least I hope so. All right, so which specifics are there when Embassy executes our tasks? And I think this is best explained by comparing the actual way the Embassy executor works to another executor, in this case, the Tokio executor. Just a quick check. Who of you knows Tokio and the Tokio executor? Well, that's actually more than I expected. So, great. Some Tokio users here. So the first thing that we can talk about when comparing executors is the number of tasks that we are actually able to run on the executors. In Tokio, we have a dynamic number of tasks that's only limited by the available RAM. Well, if we have even 16 gigabytes of RAM, a lot of tasks fits in because the task doesn't have much of overhead. Yeah, it's just that one struct, that one future struct that Rust allocates. In Embassy, the number of tasks is static. It's defined at compile time. We already talked about that. The next thing we can compare is the threads to executor relationship. In Tokio, in your application, there is just one executor. And that one executor has a number of threads that's usually equal to the number of cores in your CPU, so that Tokio can make use of your complete CPU. Additionally, Tokio brings a thread pool that's designed for blocking code. So whenever you run an operation that should be async but isn't, like, okay, you want to synchronously load a large file into memory, then you just schedule that operation to run on a blocking thread pool to not prevent other tasks from running. In Embassy, we have one executor per core, and each of these executors has one thread. That means that if we have a multi-core microcontroller, then we also have multiple executors running within a single program. Task scheduling is also something that's really different. In Tokio, we have work-stealing task scheduling, which means that each thread has an own task list to run. And whenever a thread runs out of tasks to run, it looks into the task lists of other threads, and well, it just steals one of them to execute them. This means that in Tokio, at each await point in your program, a task could be moved from one thread to another. That's the reason why in Tokio your futures need to be sent and sync, and you have to deal with a lot of pinning if you are actually doing more advanced things with futures. In Embassy, the execution model is simpler because when you spawn a task, it is always pinned to the executor it was spawned on. There is no possibility to move it to another executor. You cannot move that task from one core of your microcontroller to a different one. It will always stay there where it was spawned. And also, the Embassy scheduling is fair within the executor context. Then, the last thing to talk about is task starvation. So first of all, what does that mean? We already talked about blocking a bit. If you block the executor and stop it from doing its work, then it won't be able to switch tasks. And if it isn't able to switch tasks, then the tasks that are not currently running will never get a chance to run. So if they don't have a chance to run ever, we call them starving. In Tokio, this happens usually if you block all threads. So usually if you have as many blocking tasks as you have cores. In Embassy, the situation is a little bit different because we don't have the possibility to move tasks around between executors. If you have a blocking task running on an executor, then it will starve all other tasks that are running on the same executor. So one should really take care that you don't have blocking operations when dealing with async Rust. All right, What difficulties arise from this? Or why async can be difficult and embedded? So first of all, in the context of Embassy, we have no influence on scheduling decisions made inside a single executor. Embassy guarantees us fairness, which means it doesn't allow us to interfere with that. And we have no such thing as priorities, priority-based scheduling. There is no task better than any other task. They are all handled the same way. Then there's the general problem of cancellation safety in async Rust. A future is called cancelled when you just stop calling its poll function. If you do so, this future will never run to completion, which means that any resource that this future has allocated might not be freed, or might not be freed in the way you expect it to be freed when the future is dropped. So in Tokio, usually cancellation safety is documented. It is not a property that can be put into the Rust type system as of now, so they reverted to documenting it. There is no such documentation for Embassy, or at least I was unable to find some, which means you will always need to take care to run futures to completion. This is especially the case if you call async functions through trades, except the trade interface defines that this function needs to be cancel safe. And this is not the case for any of the async functions defined in embedded HAL Async. And then we have the whole topic of blocking the executor, which causes other tasks to starve. Well, and this brings me to the conclusion. As always in our field, there are advantages and there are drawbacks. There is always a trade-off in choosing a certain technology. In our case, Embassy offers us the possibility to have no busy loops and no polling. We have an automatic low power mode, which is especially great for battery-powered devices. Handling time is much easier, as we have seen. And we have a great ecosystem. The drawbacks are there is no such thing as preemption. So if you have a task that's really computation heavy, then it won't be much beneficial to use Embassy as a framework. Yeah? In general, async Rust makes sense for I/O heavy applications, but it doesn't make that much sense for compute heavy applications. Then we have no static guarantee for execution time, deadlock detection, things like this. This is something that some RTOSes offer, and Embassy is not an RTOS. Also, async Rust will produce larger binaries, mostly. This is why you should always compile in release mode and hope that the compiler will optimize your binary in a way that it's possible to at least fit it on your microcontroller. But this is really program dependent. So there might also be async programs that are much smaller than sync versions. And finally, you always only have a static number of tasks. So if you have a highly dynamic workload that needs to spawn tasks or threads on the way while it goes, maybe Embassy is not the best fit for that. All right, and that's the end of my talk.
Yeah, thank you very much for this amazing talk. I'm pretty sure we have some questions here. Yeah, I see Günther and then...
I've heard that you can mix Arctic and Embassy. Have you heard about something too?
Not especially in the context of Arctic, but I'm aware that the Zephyr RTOS, which is the RTOS by the Linux project, has also an Embassy executor built in. So you can run actually an Embassy executor on a Zephyr OS thread, which is probably the same direction and which is actually pretty cool.
Okay, thanks.
All right, there was a first one. I take another one here.
Yeah, thanks for the talk. A few slides back, you showed the fully functioning code, the main RS.
Yeah.
And then a slide further down the talk, you said that a task is pinned to an executor, and there's one executor per core. Let's assume you have a multi-core, so dual core or whatever system you're running on. What essentially determines where each of these tasks is run on? Because you didn't annotate it here, and
Yes.
you probably want your program to be able to compile for either one of the systems.
Yeah.
So I don't know, where would you define that?
You basically
do you
define
not?
it implicitly through the origin of the spawner. Yeah, so
Okay.
the thing is, what you're probably being after is, I said that you need to allocate the resources that you require for a task. And now the question is basically, okay, why don't I need to annotate on which executor this task is going to run, right?
Yeah.
Yeah, so the thing is, this is a single program, and the single program has a single memory space. So it doesn't make a difference where the memory lives or whether it's annotated, because each core can access the same memory.
Okay.
Yeah. So you basically just tell Embassy, okay, reserve the memory for this task, and then you spawn it using the spawner, and the spawner defines on which core it is or on which executor it is going to run.
Okay.
Do you have anything to add to that, or?
Basically, that if you have two threads or two cores, if you have two cores, then you will on each core you create an executor. So from each executor you get a separate spawner, and then through the one spawner you spawn on the one processor, and through the other spawner you spawn the tasks on the other processor.
Right. Are there any questions online? Cosme, you here?
I don't believe I have seen any questions about this talk. There was a question about that we didn't get to from the previous one, but it's been helpfully answered by one of the people online.
All right. Yeah, I think then let's.
Yeah, I wanted to ask a follow-up question on that previous question. While that might be true for memory, isn't it not true for CPU usage, right? Could I not have one very, very CPU-intensive task and like 1,000, yeah, maybe not quite 1,000, but very, very many not very CPU-intensive tasks? Is there any sort of steering on that?
No. So it's basically the way you as a programmer have to define on which core you want which task to run in that case. So you have to make sure for yourself that you balance the workload. There is no automatic balancing between task execution if you use multiple cores and multiple executors.
But to continue on that, we could just say, okay, we have this one core who is like compute heavy and just works on some tasks, like have some task spawn with a channel, and then get really heavy computing done on the other core.
Yes, of course.
You would use for I/O.
You don't also need to run an Embassy executor on the second core. You could also run maybe even an RTOS on the other core, if you like to.
Or you have like a separate chip for that, specialized for this compute. Are there more questions? Oh, sorry.
Hi. Yeah. I think one of the main benefits is also this hardware abstraction layer. So just sort of interest now in this example you gave that's pinned down to the specific chip, how much would you have to change if you want to now switch to a different chipset? Is that really just a few lines, or can you even show it because it's so simple? Is there even more?
That's a really great question, first of all. So there are some things in Embassy that always need to be specific. Yeah, for example, I told you that a task definition is not allowed to take a generic. If we now would like to pass a generic peripheral to a task, we are not able to do so. If you want to do this, you still have to define a platform-dependent task definition. And what you then usually do is you have pretty much the same as this is done here, an async function that you call into that does the actual logic of your task. And this function then again can be generic over the thing that you're putting into it. So what we would have to change in this program to have it more or less hardware independent are basically the definitions of these run red LED and run blue button triggered blue LED functions, where we would have to switch out this output here for a generic parameter and this input for a generic parameter that says, okay, this is this is an implementation of output pin, or this is an implementation of weight.
Okay, and when one does that, then the rest is really just changing the build target, basically.
Yes.
It's pretty cool.
Of course, what you always have to do is, when porting to a new platform, you will have to deal with the hardware-specific bits and pieces. Yeah, you will need to write the hardware initialization again. You probably need to use a different HAL implementation crate, things like this. Maybe even the wiring is different. So, but this depends on what the hardware guys are doing.
Right, pretty cool. Thank you, Benedict, for the great question. So I'm looking around.
We do have a online.
Very good. Go for it.
I'm not exactly clear on what the meaning of this question is, but the question is, would interrupt executor allow preemption of tasks?
All right, this is a question that we are prepared for, or at least a bit prepared for. So I omitted a few things when talking about executors. In Embassy, there are actually two kinds of executors. The one which we were talking about all the time is the thread mode executor, which is the thing that Embassy spawns by itself. And then there are different executors which can run on interrupt levels. So an interrupt always preempts the things of lower priority that are running, as it's displayed in this diagram. So for example, if we have an interrupt mode executor running on this ISR level 6 here, then it might completely preempt our thread mode executor for the time it is running. So yes, you can get a bit of preemption through this, but you cannot actually do a full context switch like an operating system would do it. Yeah, an operating system would switch out the task for a different one and later switch back to this task that's blocking the CPU. But in this case, it is not actually switching back to a different task from the thread mode executor, but to the same task. So what you rather get than preemption is maybe a bit more into the direction of having priorities.
Very well. Yeah, Thorsten.
Yes. I think in your talk, at the beginning or maybe in the middle, you explained that we have sometimes unsafe Rust code. And here in the presentation from him, we did not see any unsafe code. So I expect that the unsafe code is only in the preferential crates or in the processor crates, right?
Moment, let me navigate to. I don't have Dominic's slides available here, but I have this one. So unsafe code basically lives in everything down from the hardware abstraction layer. Okay. If you do a HAL implementation for a specific chip, then you will need to write some unsafe code to call, for example, into the PAC in order to do some register manipulation operations, and these are unsafe. So in this talk, there was no unsafe because we've always been working on top of the hardware abstraction layer, which essentially provides us with a safe abstraction. So we basically cannot shoot ourselves in the foot with that.
Okay, and maybe one additional question regarding unsafe Rust code. So often from other colleagues or from friends, I'm hearing that they said, okay, you also have to use unsafe code as an embedded developer for some reasons. For example, when you are near at the hardware or you are implementing a driver and you adjust something based on this driver, you have sometimes always this unsafe code. So do you have some arguments where you can say it's still a better choice to program embedded software in Rust as in C or C++?
Well, the thing is, you're not particularly often confronted with unsafe code. So, and still, even unsafe Rust code is still better than C code, because unsafe Rust is not the equivalent of C, but you still have a lot of type checking from the Rust compiler and so on. Yeah, what unsafe Rust gives you is basically a few superpowers to do things that you are not allowed to do in safe Rust.
Okay, yeah, thank you.
Thank you very much. That brings a follow-up question to me. Maybe you know, there's this interpreter Miri that you can use to check unsafe code. Is that also doable with unsafe Rust code?
Isn't it?
Unsafe embedded Rust
for that
code?
purpose?
Yeah, I mean for the embedded code, is there any like?
I didn't try, but I think there is.
Yeah.
Well, you will have the problem that unsafe Rust code for embedded targets is always targeting the register level. And well, these are registers that are not usually there on the CPU where you can run Miri on.
Yeah, my thought was that would be amazing to have it, but probably it's not that easy to do it. So
To be honest, I don't know.
I don't know either. That's why I'm asking. But yeah, do we have more questions? Oh, all right, Dominic.
Hi, Björn. Thank you for the talk. I have a question. Somewhere near the beginning, you showed this huge diagram of all of the embassy stuff.
Yes.
And there were a lot of stuff in there that sounds useful, like Bluetooth or synchronization. Does that only work with Embassy, these crates? So is that specific to Embassy because it comes from Embassy? Or does it also work in other embedded contexts?
That really depends on what we are looking at. So I think, but don't nail me to it, Trouble is actually only targeting async Rust. So there would be nothing stopping you from writing your own async Rust embedded executor and running Trouble on top of it. To be precise, I'm sure that Trouble is not bound to the Embassy executor because you can use Trouble also on Linux, for example. And there you have no Embassy runtime, but you're probably going to use something like Tokio. It's a bit different for probably things like Embassy time. I think this is bound pretty much to the Embassy executor, but I also think it depends on a case-to-case basis.
Okay, so some crates will work, some crates will not.
I think so.
Thank you.
Yeah, thank you very much. I'm staring at the clock, 5 minutes to 9 in Germany, 5 to 8 in UK. Given another hands of applause.